Okay, so what is this about? So Google found fail silent corruption execution errors, which we will refer as CEEs for the rest of this talk, that are happening at the CPUs and cores, and reported this at HotOS 2021. So I'll go over that paper. From what I heard, Facebook had another paper at Archive on the same thing, and this led to Google disclosing this maybe earlier and publishing it at HotOS 2021. There is a very nice talk at the link, and both Google and Facebook has been observing this for several years before they reported this. Okay, why should you care about CEEs? Previously, we had known about fail silent storage and network errors due to bit flips. That's why we have checksums in anything we transmit and in anything we store on the cloud. We have checksums because, you know, SSDs disk may have this fail silent errors. But this is the first time we are seeing fail silent computation errors. So that's new. And it's scary because this happens at some of the cores in a correlated way, and they expose us to large risks unpredictably due to seemingly minor software library changes. Let's say one day we changed a low-level Scala library that we are using for math or linear linear algebra, and then our error rate spike up. We see unpredicted errors. This is not, this is, then the company would go in a flurry to investigate what's going on, etc. It's possible that this can happen. I think it affects 1 in 1,000 servers. Google calls this Mercury cores. Facebook also gives a figure of hundreds of CPUs among 100,000 CPUs, which correspond to this 1 in 1,000 ratio. This is a high ratio. This is a high ratio. Well, for big companies, it's a high ratio, right? So they have 100,000 servers, and 100 of them would have this easily, right? We have known about CPU bugs before, right? With the famous Pentium bug. And there are so many others that are given in this link. And as the chips get more complex, and looks like the chip companies are also being on a crunch to go faster, and they are cutting corners, etc. There are CPU bugs, but they are deterministic. These are also deterministic, but only on some machines. 1 in 1,000 machines, Mercury machines, okay? So these are harder to reproduce. So the bugs in that link, you can find them, you can put a fix on them, etc. You can replicate them. These are hard to reproduce, occurring occasionally in 1 in 1,000 cores, and also hard to detect and mitigate, unlike the deterministic bugs, more deterministic bugs. And Google has already applied many engineering decades to the problem, as mentioned in their paper. Probably Facebook also did similar things. Okay, so what causes CEEs? The feature sizes are getting smaller and smaller. as the chip manufacturers like to fit more transistors into this chipsets. And we are at the limit of physical limit of semiconductors with 5 nanometer technology. Some of the gates are of the length of 10 atoms. So this could cause interaction across the gate even when the gate is not open. And the manufacturing defects manifest themselves in corner cases, not all the time. This also seems to happen 1 in 1,000 cores, and those are mercurial cores, right? So those are more prone to this. They have some kind of manufacturing defects, but this may not be detected in the test at the manufacturers because they manifest themselves under certain voltage, certain frequency, certain temperature, which are hard to test under all possible conditions. And sometimes they manifest only after post-deployment aging. With some aging at data centers, the temperature is also high. Think of this going for 6 months, 1 year in data center, and then the manufacturing defect becomes more apparent and they become mercurial core. Okay. How do they manifest themselves? The paper lists 7 different kinds as examples, so I'll read from that. These are scary. Violations of lock semantics leading to application data corruption and crashes. So you set locks, but on the mercurial cores, the block semantics somehow gets corrupt and crash things. Data corruptions exhibited by various load, store, vector, and coherence operations. Data gets corrupted when it goes through a transformation, computation transformation. This is interesting. Advanced encryption system, I think, some mercurial cores has a deterministic miscomputation there, which is self-inverting. Encrypting and decrypting on the same core works, but you cannot decrypt what is encrypted by this mercurial core at another normal core, at another normal machine. That's funny. I can't imagine what the poor fellow that observed this felt. Corruption affecting garbage collection in a storage system, causing live data to be lost. That's also scary. Database index corruption leading to some queries, depending on which replica core serves them, being non-deterministically corrupted. Repeated bit flips in strings at a particular bit position, which stuck out as unlikely to be coding bugs. Corruption of kernel state resulting in process and kernel crashes and application malfunctions. That's also very scary. Okay, are these reproducible? They are machine specific. You need to do the test on the mercurial core, and they are also condition specific. You need to find that original conditions, maybe temperature, frequency, voltage, that triggered it. The paper mentions that in just a few cases, we can reproduce the errors deterministically, usually when the implementation level and environmental details line up. Okay. The paper also says that data patterns can affect corruption rates, but it is often hard to tell. Okay, so let's talk about detection and mitigation. How do we detect and mitigate CEEs? For data corruption at storage networking, it's easy to detect because the right result is the identity function. We like to see what we sent to be received. We like to see what we stored to be retrieved, right? So we know what we want to check. and we can use checksum because it has to be the same information. So the checksum should be preserved. Either if this is corrupted and checksum is fine, we know something was wrong. If checksum is corrupted and this is fine, we still know something is wrong. It's easy to detect them because they are not being, what is it called? They are not being transformed, okay? But during a computation, things are being transformed. We don't know what is the result unless we compute it, right? So because of that, it's hard to detect and correct CEEs. Automatic correction seemingly requires triple modular redundancy. What is triple modular redundancy? You do it on 3 cores, and they should all agree. If one of them is wrong, the other 2 agree, then you copy from the other 2. This is automatic corruption. Okay. This is still with 1 in 1,000 error rate. This is still a little scary. What if 2 of them are mercurial and they agree? Maybe they would not necessarily agree. That's but maybe they do. I don't know. Maybe they are mercurial in the same way. I don't know if that's possible. Then even that is flaky in, less than 1 million, 1 in a million chance. But 1 in a million is not a rare number in cloud computing terms. Okay, another thing about this is that, when we are corruption checking over blocks of data, we do it over chunks of data, we use checksums, the cost is amortized, but here we have to do it per instruction. So that is not, or we can do it maybe per multiple instructions, but we need to maybe come up with blocks of computations to check for. This is new. Yeah, this is new stuff. So what can you do immediately? I guess end-to-end checks still would help, right? So if you code more defensively, write more assertions and tests, if you use information about what you are trying to compute and check that at least it should be in these bounds, or at least it shouldn't be null at the end or something. When I check, initially it was this, so I expect it to be this after the computation. Those could be helpful. Yeah, so I guess not much. Double check center of code when checking is cheaper than computation. Identify cases where checking is cheaper and not skimp on doing checks there. So Facebook has an archive paper on this. They said that they have observed CEEs over several years. They also say that the rate is 1 in 1,000 rate. Their paper predates the Google paper on archive. Google paper published first at AutoS. Another thing the Facebook paper claims is that CEEs are not limited to CPUs. They are applicable to special function accelerators and other devices with wide data paths, meaning GPUs. Okay, machine learning already is a black box, hard to debug, hard to penetrate, and I don't know, with these glitches, what chance we have, or maybe since machine learning has a sort of a self-stabilizing nature over training, maybe the effects at GPUs or machine learning hardware is not as severe as a computation error. I don't know. Nice thing about Facebook paper is that it's a longer paper. They go into more details. The Google paper doesn't go into details. Pretty much what I told you is what is in the Google paper. The Facebook paper shows a real-world example where they detected CEE causing data loss. This is in a Spark deployment. This is a simple Spark workflow. It goes through this. There is a decompressed file size calculation, and the file is written to database if the size is greater than 0. This calculation uses Scala matpov function, which at the mercurial cores, which is 1 in 1,000, results in 0. So the file size is more than 0, but on the mercurial size, it's computed as 0 due to this bug that is triggered only at the mercurial cores, not at the other 999 CPUs over, let's say, 1,000. So this is silently omitted from the database. So we are having data loss because we are ignoring these results that should be reported as not reported. Okay. They root cause the bug going deeper and deeper. They first occasionally run into this issue, right? So maybe if this is run over tens of thousands of machines daily, you see the issue that's always there, right? So this should be really hard to debug, right? First you notice and you get irritated by the issue. It's always there. You look into it, you don't find anything, but the issue is there. It drives you crazy. Then you get some hints maybe somehow that this is in this code block. Something is happening in this code block for some machines. And if this was deterministic, it's easy to do, right? In 999 machines that you try, it works, but you still get daily reports of data loss. And what do you do? So somehow they suspected the matpov function. Okay, so at one of the cores, they were able to reproduce. I guess they somehow pinpointed, they somehow suspected a mercurial core and was able to reproduce this and see that, okay, this core is faulty with the same thing under certain conditions, maybe not always also. Then they go deeper and deeper in the JVM, and they add debugging statements. They parse relevant functions, and they narrow this down to mat.pov function in Scala library. Maybe they also had a hunch that, oh, this library was recently changed or something, I don't know. And then they were able to even further narrow it down to a faulty instruction in some registers. Okay, so that's pretty much my presentation. It's a scale kind of failure. It's being non-deterministic or being deterministic in a small fraction of computers in certain fraction of time and conditions is what makes it more scary. This is not as severe as Byzantine cores. But Byzantine failure is anyway formulated to take care of very peculiar failures like this. So it could be used, that model, but Byzantine fault tolerance is costly. This is also costly, as you know. I think this is less severe than Byzantine failures because this only manifests in certain computation units maybe, and it's not a full-fledged malicious node, right? Byzantine failure makes that abstraction of let this be malicious node, and let this be a node that can arbitrarily deviate from the protocol. This does not arbitrarily deviate the protocol. This deviates at certain low-level instructions for the protocol. So I think practically is it can be addressed in a less, in a more efficient way than Byzantine failures, because it is not as severe as Byzantine failures in practice or practically. But yeah, here we are dealing with fail silent computation errors. Okay, so we can go to question answer discussion.